Thank you very much. In this talk, I want to present questions, mainly problem and questions, mainly in geometric analysis. And I would like also to describe some recent techniques to deal with those. And this is the setting. I want to consider smooth Riemannian manifolds. Here, G is symmetric. And the general question is how to understand the shape of a space of a Riemannian manifold under constraints and bounds on the curvature. This is a pretty classical question, and interesting bounds on the curvature are listed here. The first one, which is the weakest in this set, is a lower bound on the Ricci curvature. One can also consider bounds on the Ricci curvature and up and lower bound on the sectional curvature. I'll be mainly interested in the lower bound on the Ricci curvature. And natural questions here are the following. One can try to understand how these bounds affect the geometry of the space, the topology of the space. So in particular, one would like to understand consequences of the level of fundamental groups, homotopy groups, homology groups, homeomorphism and diffeomorphism type. And last question, which has a more analytical flavor, is about a priori estimates. Given a bound, one of these bounds on the curvature, what kind of other geometric and analytical quantities we can control. And you can, if you want, you can think of it as a PD estimates. Here, instead of having a solution to an equation, we have a super or sub-solution to a linear equation, which is the curvature tensor, and you ask which quantities you can control a priori. And so in order to give a little more concrete idea of what I'm talking about, here I'm listing two very important conjectures in this field. Let us consider manifold with non-negative Ricci curvature, so the weakest assumption. The first conjecture is due to Milnor. It's a very famous conjecture, and is about the structure of the fundamental group of manifolds, possibly non-compact with non-negative Ricci curvature. And one would like to prove that the fundamental group is generated by at most Cn elements. Here, Cn is a constant depending only on the dimension, and this is widely open. The second conjecture I would like to present is Yau's conjecture, and it is much more related to a priori estimates. And here we ask whether a lower bound on the Ricci curvature alone is enough to get an upper bound in the L1 sense. And in the remaining part of this talk, I will focus mainly on results, conjecture, and theorems related to Yau conjecture. And I would like to use this kind of questions to motivate the introduction of non-smooth techniques in this field. And I would like to convince you that even though here I'm dealing with smooth objects and all the statements are about smooth manifolds, there's hidden here a world of non-smooth objects, which is very interesting. And to do so, I want to present a very toy problem, very simple question. Pick a function, smooth. Here, the analogy is that the function is our Riemannian manifold, and assume some bound. This is an L2 bound on the gradient of f. Now, very simple question. Can we conclude that the gradient of f is bounded? And here the analogy is simply that f is a smooth function. In Yau conjecture, we have a smooth Riemannian manifold. We are assuming a bound which does not depend on smoothness. We use smoothness to break down this bound, but actually it doesn't depend on smoothness. And this is the replacement lower bound of the Ricci curvature. And we ask whether another estimate, the L1 norm of the Ricci curvature in the previous conjecture, must hold or not. And of course, the answer here is no. And the reason is very simple. Everybody knows that the W12 norm is not strong enough to control the Lipschitz norm, of course. But let me explain what's the thinking process behind this very simple answer. And the thinking process is the following. So first, we observe that this bound is enough to get pre-compactness. If you pick a sequence of smooth manifolds satisfying this bound uniformly, then you can extract limits in weaker topologies such as L2. And now you understand that limits are no longer smooth. And this is because functions satisfying this bound are not actually really smooth. So you are assuming smoothness, but the real nature of functions satisfying this bound are not the nature of being smooth, but is the nature of a Sobolev function W12. Now, at this point, you have a full understanding of functions in the space W12 of limit points with limits point in the L2 topology under this uniform bound, and you can simply build a counterexample to the previous question. Okay, we can try to play the same exact game in the setting of manifolds, in the setting of the Yau conjecture. The first thing we need is some compactness. Our bound on the curvature that we assume should be able to produce some pre-compactness at least. And this is possible. This is a theorem of Gromov, 1981. It says that the weakest assumption among the curvature bound I mentioned is enough to get limits out of any sequence in the so-called Gromov-Hausdorff topology. And the Gromov-Hausdorff topology is induced by distance, the Gromov-Hausdorff distance, and is a generalization of the standard Hausdorff distance between compact sets of the Euclidean space. And you should think of it as a zeroth order notion of convergence. So the Nonsmooth structure here is really comes into play. And in particular, there's no hope to expect that the limits point are smooth Riemannian manifolds. Okay, once we have these limit objects in complete analogy with Sobolev functions in the previous toy example, one may ask several questions. The most natural one is about the structure of these limits, and in particular, one looks for epsilon regularity theorems and estimates on both the regular part and the singular part of the spaces. And also, it is very interesting to try to understand what properties, what quantities can be passed to the limit. In particular, it will be interesting. It's very interesting to understand when limits have a manifold structure and when the manifold structure passes to the limit. Same question for topology. And in the case of collapsing, one may try to do something a little more complicated along the lines of Yamaguchi vibration theorem. And the last question I want to mention is about the synthetic notion on these non-smooth objects of lower bounds on the Ricci curvature, sectional curvature, or any other curvature bound. The idea is that these limit spaces are not smooth anymore, but they have properties typical of spaces with bounds on the curvature. But you don't have the structure to compute the curvature and say, okay, here the bound still hold. And the question is, can we find a set of conditions, a set of synthetic conditions to rule out among metric spaces the ones with a reasonable weak notion of curvature bound? And there are at least two very successful theories here: the theory of Alexandrov spaces about lower bound on the sectional curvature, and the much more recent theory of CDKN and dark CDKN spaces about the lower bound on the Ricci curvature for metric measure structures. And each of these questions has given rise to essentially a huge research field, and there are many results that, of course, I cannot present in 15 minutes. Just wanted to share questions and keywords, hoping that someone gets interested. Okay, so at some point I want to go back to Yau's conjecture and present the theorem, a recent theorem by Jean Neighbor, which gives an L2 bound on the sectional curvature under slightly stronger, actually really stronger assumption. Full bound on the Ricci tensor and the non-collapsing assumption on the volume. So this theorem goes in the same lines of Yau's conjecture, but we have stronger assumptions and a much stronger conclusion. And I would like to give some idea of proof, or at least I would like to list ingredients of proof. And the point here is that the key idea is to study limit spaces and essentially apply the same strategy we have seen in the toy model from before. And those are the ingredients. The very first step is the understanding of limits of manifolds satisfying a bound on the Ricci curvature and the volume non-collapsing. And it turns out this has been proven by Chigan and Neighbor in 2015. It has been a conjecture for a very long time. It turns out that these spaces may have singularities, but those singularities have codimension at least 4. The second step is about the understanding of the regular part of the space. And here there are epsilon regularity theorems saying that if the ball of radius 1 of your space is close enough with respect to this Gromov-Hausdorff topology to some model, you should think of models like the Euclidean space or cones with the singularity of codimension bigger than 4, then you get a lower bound on the injective radius and the harmonic radius. So in particular, you can get out of simple elliptic estimates good bounds on the sectional curvature on any ball satisfying this condition. Now the point is how to glue all of these estimates together and conclude an L2 bound. And this is the last step, in which effective covering based on the understanding of limit spaces have been proven. Last example, this is a theorem I proven recently with Andrea Mondino and Daniele Semola. So here we study manifolds with non-negative Ricci curvature and volume non-collapsing assumption. And the a priori bound here is not on curvature operators, but is in terms of this object. I don't have time to explain the full meaning of this object over here. The idea is that this is a family of measures depending on R, and this family of measures has strong relations with the boundary measure of the manifold itself, and this bound can be obtained also on manifolds with boundary. And there are connections with the geodesic flow and the Liouville measure on the tangent bundle. The most interesting application of this estimate is in the setting of Alexandrov spaces, which is a class of non-smooth spaces with sectional curvature bounded below. And what we can prove out of this result is that a long-standing conjecture, we complete the proof of a long-standing conjecture by Perelman and Petrunin about existence of infinite geodesics on any Alexandrov space. And yeah, thank you for your attention.
Are there any questions, Rana?
Yes.
So what are these infinitely many geodesics? Are they complete?
Again, sorry?
Are they complete geodesics or?
Yeah, are metric geodesics. Metric geodesics in a sense that a curve which is minimizing at any peak to points, the curve is minimizing among these two, locally minimizing.
But it must be some, I mean, the thing that you prove that there are infinitely many are some global objects, I guess, right?
The point is that what you want to prove is first you try to define an exponential map, and you want to show that you can continue geodesic forever.
I mean, like, my question is sort of I think simpler than that. So are these infinite geodesic lines? That's what you mean by?
They can close, and they are locally geodesic. They can close.
Okay.
The point is that only the boundary of the space in the setting, only the boundary of the space can stop.
So I guess my confusion is on the objective infinite.
Yeah, it's defined for an infinite interval of time.
Okay.
But it's not globally geodesic. It can close and
Sure.
But it's defined for an infinite set of time. So yeah, that's the.
Okay. So they're like either an infinite line or a
something that close out. Yeah.
And so what is the statement? Any Alexandrov space has at least one?
Actually, there are infinitely many.
Okay.
Yeah. At almost any good point, regular in suitable sense. And given a good point and a good static direction, you can find this geodesic that goes on forever. Which is a weak you can construct a weak exponential map almost everywhere. You can construct a Liouville measure, and it turns out that the Liouville measure is preserved.
Almost every word is in which sense? Category theory, method.
Yeah, there's a measure here. The measure is the standard volume measure. So in the smooth setting will be the standard volume measure. In the non-smooth setting, you get some reasonable measure out of the theory, which plays the role of the volume measure. Yeah. And the standard regularity theorem here for non-smooth spaces says that with respect to the volume measure, all points are regular in a certain sense. You can have singularity. Sometimes the set of singularity is just negligible. In other setting, you can prove that it has small codimension. And you can go down with codimension and control by means of other measures. Yeah.
So for these theorems, like what kind of examples should I have in mind? I know when people talk about Ricci flow, they often tell you about these dumbbell manifolds. Like, is that a good example to keep in mind? Or
okay, so I mean, in the setting of say Alexandrov spaces that are non-smooth spaces with sectional bounded below, the simplest singular space is the cone, really the ice cream cone. But you can think of a boundary of convex subsets over n. You may have conical singularity, and these are perfectly nice Alexandrov spaces. And if you don't allow collapsing, something specific, essentially all the singularities are conical. If you allow collapsing, the situation is much more complicated, and yeah, there's no simple description of singularities in general. Yeah.
So is the geodesics that you construct that may they run into singularities or
no? They cannot.
So somehow even in the proof there's the fact that
there's
many of them which are just simply not hitting the singularities.
The fact that the regular set the fact that the geodesic cannot run on a singular point in the non-collapse setting when you have conical singularity is pretty clear, because a geodesic running on the tip of a cone would split a line in the tangent cone. More in general, but even in the Ricci setting, you can prove that the regular set is convex in this sense. So you can pick 2 points and connect with it.
But that must be because, for instance, if I take, say, a convex set, which is like, say, the union of 2 half planes, actually from the geometric point of view, that is not really singular.
Yeah, you cannot.
Because the ridge is actually a flat point.
Correct. Maybe, so you can glue together 2 manifolds along the boundary. And so essentially here the space is flat. So you may have at the second order some singularity, but you don't have conical.
So the geodesic might run into it and simply just go past. But for you, it's a regular point.
For me, it's a regular point, yeah.
All right, let's thank Elia again. We've read material project on robust sublinear expanders.
Thank you very much. Thank you all very much for coming. So my name is Matija Bucic. I'm interested in probabilistic and extremal combinatorics, but also very much in finding applications of combinatorics to other fields. So at any point in your own work, you run into something vaguely combinatorial sounding, very happy to hear about. So anyway, today I want to tell you something about expanders or expander graphs in poles. So this is one of the perhaps most widely useful class of graphs that people looked at, and they actually have quite a few practical applications such as network design, chip design, but they are also very often useful in theoretical work and absolutely invaluable in combinatorics and theoretical computer science. So there is an amazing survey by Hurey, Lineal, and Vigderson on over 100 pages detailing various applications and cool properties of these kind of graphs. I very much recommend it. Avi is not here, but you can also ask him in general. He is an expert. Anyway, so let me tell you a definition, and I'll draw a picture explaining a bit what I mean by an expander. So graph G is a lambda expander if for every subset U of the vertices of our graph, which is not empty. So these are some kind of very silly conditions just to avoid some kind of contradiction, easy contradictions. So it should not be too big and it should not be empty. Then what you want from it, then you want that its neighborhood here. So you want that its neighborhood is bigger by a factor of lambda than the size of the set itself. And the neighborhood here is set of all vertices with a neighbor in the set U that we're looking at. So let's look at the picture. I think it's far more illuminating than the definition. So here's our graph G. We want to say that it's an expander. So what do we want from it? We want that if you look at any part, any set of vertices in your graph, if you make one step out of it, so you just look what you can reach by doing one step going out, then this is bigger by a factor of lambda than the size of the set you started. Okay, so in this sense, you are expanding by doing one step. This is why they're called expanders.
Lambda should be below 1 or above 1?
So usually, so that's kind of the point of the talk, but usually you work with lambda being at least a constant and preferably even bigger, because that gives you a lot of cool properties. So everything that I mentioned kind of you get with lambda being, you need lambda to be big for many, many of the properties of expanders. But somehow the point of sublinear expanders is that you can take lambda to be smaller and this still gives you some information and useful stuff. I'll get to that in a moment. But for now,
When you say neighborhood, does not include you itself.
yes, so I'm talking about external neighborhood. So when lambda is bigger than 1, it doesn't actually matter. When you go into sublinear words, it starts to matter. Thank you very much. Yeah. So not in you would not you itself. Very good. So these are expanders. So a priori, it's completely unclear why this kind of expansion condition is useful for anything. So let me tell you a nice short proposition, which will at least explain on some level one of the actual practical applications of this. So any two vertices in, say, a 2 expander are a distance at most 2 log base 2 of n. N is the number of vertices of the graph. It's again a picture. Yeah.
You had an upper bound in the size of U lambda over 2. If it's a 2 expander, that means that you can be the whole of the graph.
Yes, I think what I wanted to say here is thank you. Yes. It's really kind of use, yeah, what you want to prevent is taking U the whole graph. Because if you want the whole graph to expand, you just don't have anything else where you can go. So this is why this exists. It's really kind of a detail which never actually comes into play when you do it, but you're perfectly correct. Thank you. I think now I said it correctly. Yes, that should be the conclusion. So anyway, so this proposition tells you, again, a picture maybe tells you a bit more than words. So if you take your expander and you take any 2 vertices inside of it, there is a short path which joins them. So this is also called, the graph has a small diameter, at most 2 log 2n. And not only that, but if you assume a little bit stronger expansion than this, then you actually get this with certain resilience, robustness properties. So not only will you be well connected, but you'll be well connected even if you delete some edges from this graph. And by now you already can maybe see why this is useful in designing networks. Because if you want a network in which you can quickly reach from anyone to anyone, and it's also resilient to outages if storms or whatever breaks your cables, then you can still do it. And so people actually use expanders to design and build networks based on this kind of ideas. The key thing that I didn't mention so far is that you can actually build them with very few edges. So you can find very sparse expanders, which still have all of these properties. So the network is also cheap to build. You don't need many cables. So anyway, that's a kind of just picture to have in mind, one application and one exact proposition. So what I have in mind for today is to tell you about the direction which was of more theoretical nature and useful in theory, and to prove some kind of nice results. So the idea dates back to Komlos and Semeredi about 25 years ago. So the general approach, how you might want to use this kind of expanders is you start with an arbitrary graph and you want to find some structure inside. That's a general type of problems that we look at. You can also work with other structures, but I'll focus on graphs today. So a natural thing to try to do is maybe you can find an expander in your graph. If you can do that, then maybe all of these amazing properties that I didn't tell you about, can use them to find your structure in the expander. So expanders are super nice graphs. They're very useful. We understand them very well. Well, to some extent very well. We can use them to build things, to find objects inside our graph. So the problem with that is that it's not easy or even possible in certain cases to find strong expanders in an arbitrary graph. So you'll not be able to find the log n expander in an arbitrary graph, which keeps the same kind of size density as the graph has. So what they introduced is, okay, you cannot do that, but what you can do is precisely what your question was getting at. You can find much weaker expanders in any graph. So let me do a definition. An expander is sublinear. If lambda is tending to 0, so you should think of lambda, say, as being 1 over log squared, and everything that I'm going to say will be true for that choice of lambda. And the key property is that any graph contains a sublinear expander of about the same density. So you can run this paradigm of pass to an expander, use it to find your structure, but what you need to do is you can only work with these sublinear expanders. You will not be able to get the full power that might want. And the main problem with sublinear expanders is that they lose this robustness properties that I mentioned. So you will not be, in some sense, robustly well connected as you were here. Because imagine where we're working with 1 over log squared. So imagine that you have a set of size log squared. And sublinear expansion 1 over log squared only guarantees you one vertex connected to it, and it can be connected by a single edge. You remove that edge, you're disconnected. The network, you got nothing from your net. And these kind of issues are really problematic with sublinear expanders. But even despite that, they were extremely useful. There is now quite a list of conjectures and results that were proven and solved using these sublinear expanders over the last 10, 15 years. Perhaps the thing to highlight is a resolution of a 40-year-old conjecture of Erdos on odd cycle lengths, which was done by Liu and Montgomery. So this paradigm has actually been quite useful, even just working with sublinear expanders.
When you say contains, you want to have all the vertices?
I want it as a subgraph. So I want to find in my graph some subset of vertices, and then you would want to have as many, you keep all the edges, because more edges help you to expand. The more edges you have, you expand. So this it's induced, so if you want, but yeah.
I'm sorry.
Yeah.
But then, like, if I just take 2 vertices and an edge connecting them, like, I think I'm missing something. If you just want to find a sublinear expander, you can find one which is super small.
So 2 vertices and so yeah, I mean, for sublinear expanders, I agree. You want to keep the same density, and you probably want to keep something else. But yeah, so for 2 vertex thing, you are right. But yeah, it needs to be a bit big. And when you're working with just sublinear expanders, you also need to ensure something like minimum degree things. And so somehow, in order for it to be useful, you need to keep something more than density. Density will be okay for robust sublinear expanders. But again, you are correct. I should probably be more careful. I mean, the idea was just to kind of give you a flavor of where all of this was coming from, not so much to go into details. But good. So now finally I get to the robust sublinear expanders. And this is, so the idea is, again, due to Komlosh and Semeredi, they had two papers coming one after another. So the idea is this kind of pictures are very bad for you. You don't get robustness conditions for free from sublinear expanders. But what you can get is you can, in addition, ensure robustness on top of these sublinear expanders. So let me modify this definition on the top board into a definition of robust sublinear expanders. So now this becomes something explicit, and I'll just plug in specific numbers, and I'll change lambda expander. So a graph is said to be a robust sublinear expander if whenever you take a subset, which is again not too small and not empty and not too large, then either you get what we had before, just with an excellent, really, really good expansion condition. So in this case, you're really expanding very well, or you get that you maybe don't expand at all well, you just expand sublinearly, but you do it in a certain very robust way. So the robust neighborhood of U has size at least size of U over log squared. And what I mean by robust neighborhood is set of all V, so all vertices which have at least D neighbors inside of U. And you should think of D as being something like log to the 4n. Okay, so again, pictures are better than words, I think, at least for this kind of thing. So in the first case, what you get from your set U is that it expands really extremely well, but you only have maybe one edge from every vertex going there connecting to the set, which is first case. In the second case, you have your set, which expands kind of tiny amount. But what you have is that every vertex, or almost every vertex here, sends many, many edges going back, not just one. So in some sense, it's again hard to disconnect, because in order to remove a lot, you need to remove all of these edges to disconnect this piece from your graph. And this definition is ours. So this is with Richard Montgomery. And there are several competing ones, which have also found several applications over the years. And in particular, I like this one because it gives you the robustness from the definition of expansion rather than a separate condition. And it also led us to proving several very useful properties of these robust sublinear expanders, which are generally easy or much easier to do in normal, really good expanders. But you can get them in these things, which you can find in any graph, and then you can use them. You can actually even decompose any graph and almost decompose into this kind of thing.
Sorry, so constant valency graphs are never.
So this is a specific choice of parameters which we worked with. You can adjust them and still get some kind of statement like that, but we are generally going to need to pay some kind of polylog factors if you want to find it in any graph. So you can develop the theory of this, but with this idea of how we want to use this, we already need to start paying some polylog factors there. And you'll not do better than this 1 over log squared n. And in general, the main idea, driving force, why we developed these things and worked with them is because we wanted to attack an old conjecture in combinatorics called the Erdős-Galay conjecture, which says that if you take any n-vertex graph, you can decompose it into just linearly many cycles and edges. This is about 60 years old. It's really central. People looked at it a lot. There are a lot of results, partial results, classes of graphs for which it's known, related problems for which we know the answer. And what we managed to do using this machinery that we developed is to get very, very close to it. So prove it up to a log star n factor. So log star is iterated logarithm fact. So this is this incredibly slowly growing function. So this is joint work with Richard Montgomery. And in some sense, it seems not so clear where these two things connect. So let me use the opportunity to shamelessly advertise that I'm giving a much longer version of this talk next week, where I'll hopefully be able to explain a bit better how all of this ties into this kind of problem and how this can be useful. Thank you very much for your attention.
Are there any questions?
Is it still true that you can find a robust sublinear expander in fundamentally any graph?
Yes, so with these parameters, yes, you can even decompose any graph if you're willing to sacrifice n times polylog and many edges. So we can decompose into just normal sublinear expanders by paying nothing, but if you want robustness conditions, then you need to start paying edges. I mean, need is a strong word. The thing is, many of the things that we're proving might be true in sublinear expanders. And if you can do that, then you prove that conjecture pretty much immediately. So the problem is that these things are super hard with normal sublinear expanders. And this gives you a lot of power and almost brings you back to the normal, like big expanders. Because in terms of edges, they're actually expanding well. But you can find them in any graph is really and even decompose graphs into that. Thank you. Yep.
Are those pictures dual to each other, the two pictures you drew in some sense, or?
So they're the two outcomes you might see for a subset. So you cannot exclude either of them and both will happen in a certain way. So actually this picture appears inside of this one if you look a bit closely. But so somehow if you take a random subset of this one, you will find some small set which expands really well inside of you. It's actually a very good, I mean, that's useful in certain things that we're doing, that somehow everywhere you're actually seeing this super good expansion picture. Just not that you can say that it's true everywhere for every subset. But yeah, so they're not dual, but they are very, very much related. There are two different cases which you might be seeing in your graph. Thank you.
All right, let's thank the GIS.